Good. So the bigger and better things are direct proofs. And before we start proving things, we need to have things to prove things about, right? We need to have subjects that we're proving things on. So that sounds weird. Not human subjects. We're talking about mathematical subjects. And so what I'm talking about here is, let's get some background info. And first, let's talk about important sets. All right. So remember, sets are just collections of things. And some very important sets are the following. So we have the natural numbers. I'll say for the natural numbers, which we give this cool looking N symbol with like a bolded one line there. And what that equals is that's just all your counting numbers. So that's 1, 2, 3, 4, 5, ... So I'll say these are counting numbers. Makes sense. You guys probably heard some of this before. And then we have the integers, which we read as a Z with a cool looking thing like that. And these are the counting numbers, 0 and the negative counting numbers, all kind of like these whole numbers, positive and negative. And so that could be like -3, -2, -1, 0, 1, 2, 3. It goes on and on and on in that direction. So these are all the counting numbers and 0 and all the negative counting numbers, right? And we should all kind of have a grasp what the integers mean and what they are. And the integers are really our starting point for this entire class. I kind of said earlier, I think, in one of my lectures that everything needs to come from some kind of starting point. The integers are our starting point. And so we may assume we know how these work. Specifically, so specifically, we can make the assumptions. We are allowed to eyeball if a number is an integer. Or I guess more formally, I could say you're allowed to identify a number as an integer. And by allowed, all I mean is that if you're doing a proof, right? If you're doing a proof and you get down to x equals 2, you can go, okay, 2 is an integer. You know 2 is an integer. You don't have to prove beyond that 2 is an integer. And we'll talk later about things that you will have to prove, right? So the point is you're allowed to identify numbers as integers. That's fine. You can use that the integers are closed under addition. And what does the integers being closed under addition mean? First of all, what does that sound like it means to someone that's never heard before? Does it sound like no shirt, no shoes, no service? Like, does it sound like they don't work? So the integers are very open to addition, but what it means is that closed under addition, which means that they're open to the concept, but they're closed under it, which means for all A and for all A and Z and for all B in the integers, A plus B is in the integers. All it's saying is if you add any two integers, you're gonna get an integer. So it's closed under addition. What that concept kind of means is that you can't get out of the integers just by adding two integers together. Now you can also assume that N is closed. I should say is here, because even though there's infinitely many natural numbers, the set itself is just one thing. I'm saying the set is closed. So N is closed under multiplication. So for all A and Z, and for all B and Z, A times B is in Z. Same concept, right? You multiply A into integers, you're gonna get another integer. So here's a question. Is N closed under division? What do we got? Lauren says no. Why do you say no, Lauren?
Because can't you divide two of them and get like a really long decimal?
Exactly, right?
Or any decimal?
Yeah, it doesn't have to be a long decimal, right? Example, 1 divided by 2 equals 0.5, which is not an integer. And remember, we're allowed to identify integers, right? So we kind of just proved that. Oh, you guys can see that. All right. And then the other thing you're kind of allowed to assume is, actually, this is good. This is it. So the integers are our starting point, and these are the things we're allowed to assume about them. Literally, basically, everything else in this class, we will prove to be true. So no more assumptions anymore, right? We're no longer relying on our intuition or relying on anything. We're basically just relying on what we have right here, what I've written down right here are facts, and relying on our logic that we have, the logic we've built our foundation on the last like 4 or 5 weeks or whatever, and algebra. You're allowed to assume how algebra works. Like you're allowed to assume that like if, and also say in general, can assume you know how algebra works. So for example, if you know x plus 2 equals 5, then you're allowed to do that implies that x equals 5 minus 2. You can subtract 2 from both sides to get that x equals 3. Right? You can do algebra like that, or you can do something like how x plus 1 is greater than x, that kind of thing. But other than natural numbers, logic, the things you know about the natural numbers, or sorry, integers, logic, the things you know about the integers, and algebra, other than that, everything's going to be defined and proven from the ground up. Who's excited? I mean, come on, this isn't that much, right? We're not really assuming that much, and actual math assumes a lot less than this. Like actual math like starts down here, we're starting like right here. So we're starting a little above actual math, like actual like formal mathematical logic derivations, all that kind of stuff. But the point is the things you do with this, like all this goes down, that goes down, 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 and we're gonna go all the way up like 30,000 stories to get to modern math. Okay, so let's get started. Let's start climbing. So let's first define some more important sets. So Q is going to be the set of all things that looks like A divided by B, such that A is in Z and B is in Z and B does not equal 0. Other way to put this is just all fractions. Why is this important?
If p is 0, then it's going to be invalid.
Yeah, you can't divide by 0, right? You're going to get something that's undefined. We can talk about that later, but dividing by 0 literally means undefined. It just means we don't have a definition for what it means. And I hope you guys are starting to get some more context for what undefined means, because literally everything else is defined. This is the, I'll put little things here. This is the definition of the rational numbers. This is defined from the integers. And you have to use like things like ands, right? Our logic operations come back. So it kind of uses everything. All right, the real numbers. You don't have to know this, but I think for some of you that have taken calculus, it's interesting. The real numbers are literally defined as being the limit as n goes to infinity of x subscript n, such that for all n in the natural numbers, xn is in the fractions. So what this means is that the real numbers are the set of everything that's a limit of rational numbers. So any sequence you can make with rational numbers, oh, I should call these are rationals, by the way. These are the rational numbers, and these are the real numbers. Good. So, yes, the rational numbers are just fractions with integers. Real numbers are limits of rational numbers. You don't need to know that. This is just some high-level technique stuff. What real numbers really are, the thing that you can think of it as, is all numbers on number line. That's all they are, right? And no real gaps. For example, you know, you have 0, 1, -1, 2, 3, 4, -2, -3, all that, right? If we just took the fractions, well, we'd be missing like pi, for example, which isn't a fraction, but it's on the number line. So the real number is all the numbers on the number line. So the irrational numbers, we don't have a symbol for. We actually just write them as R, and then we do this backslash Q. And what do you think that means right there? Come on, who's got me? How would you describe an irrational number? I'm getting the sensation that a lot of you are thinking, I wouldn't describe irrational numbers. I would never dare. But if you had to. This
B with
Big
the
scale.
limit, B multiplication the limit and divided by A, if we put it like that.
Oh. I was gonna write I was gonna say it a lot simpler offer, but you could do something like that. I was gonna say that irrational numbers are just real numbers that aren't rational. That's it. Right? I mean, irrational numbers, you might think of them as decimals that like go on forever and never repeat, that kind of thing. But decimals that either stop, so decimals that terminate or repeat, that's exactly what the rational numbers are. So the irrational numbers are just everything that's not a rational number. So these are just all non-rational real numbers, like the square root of 2, pi, e, etc. All right, any questions in this background info? I think this is also we heard before, is maybe put in a more formal context. The point is, though, right now, we don't really know anything about the rational numbers and the real numbers other than these kind of definitions. Everything else about them we are going to prove, which is awesome. So, first things first, though, we have more definitions.